Hello everybody, how's it going today? My name is Connor, welcome back to another video. Today I have a very special project to show you guys. This is something I've been wanting to show you guys for a long time now. It's something I've been kind of had in the works for the past couple of weeks. And I haven't really made a video about it yet, other than the little teaser I put out earlier. Um, this is something that like I said, I'm excited to share it with you guys. I've been excited about working on it. It is something I'm calling wigglers. And as you can see, the little dudes here, they are indeed wiggling around. So, um, what is this thing? This is a deep reinforcement learning project. I wrote it in Rust, as of course, and it's using Bevy game engine for the graphics and for the physics, and it's using the Burn neural network library, Burn neural network crate machine learning crate that is pretty new still, but I've been enjoying my time using it for the most part. I've tried a few others like DFDX um, and the torch bindings directly to Rust, and they just haven't been great. So anyway, what is this? What are we looking at here? Let's talk about this. So this is what you're watching is a bunch of AI powered, independently operating reinforcement learning agents that are basically fighting to the death. They are um, they are trying to kill each other. They're trying to stay alive as well. If you're familiar with reinforcement learning at all, you'll know that there's usually a reward function that is or reward value that is given at every time step to the agents um, in order to help them learn what to do. So in this case, they are rewarded for getting kills, for reducing the other agent's health to zero, and we're also rewarded for hitting their shots. Just to kind of encourage them to not just hold down the fire button, you know. Um, so, and then they are punished. They get negative rewards for dying and for missing their shots, and that's about it in terms of what their rewards are. So, uh, So, what do we have here in the interface? Well, you can see obviously we have the agents in the map over here. The blue side and the red side don't really mean anything yet. Uh, that's from an upcoming feature where I kind of want to add something like capture the flag for them to do. But I'll get to that later. I just wanted to finally get a video out for you guys before I added any more to this monstrosity. So, you can see here that each agent has its own name, has its own identifier, like the little 2 Javier, 1 Angelo, 0 Sheldon, 3 Richard. Um, that's just in case they end up with duplicate names because it just pulls randomly from a pool of names that I generated online. Although there are uh, few agents in here, a few names that I can be pulled from that are named after some of my friends. So shout out to them. None of these are named after any of my friends. None of these ones are in particular, but occasionally it'll pull a name from that selection. So above each agent, you can see which direction they're facing by the debug. That's just the default or the regular debug overlay from Bevy Rapier, which is a physics engine I'm using. It's convenient to use. So and helps me to learn what they are actually seeing. So helps me to figure out what they're actually seeing. So yeah, you have their little health bars. They got little red health bars above them to indicate their health. The little white lines coming out of them are their shooting. So if that white line hits another agent, then that agent will take damage, and they'll know that they've taken damage because their health is one of their parameters that they get input into their neural networks. So excuse me. So um, and then up in the top, we have their scores. We have their kills and then their deaths. Um, and then to the right, we have a log showing just kind of training metrics and a kill log as well. It's a text log for general text information. To the bottom, we have something interesting that I've kind of whipped up. This actually shows what they're currently thinking, basically. And I'll get into what that all actually means in a bit, but this shows their current action outputs, and it's color coded based on the probability distribution that they use. Again, I'll get into all that in a sec. So that's what's going on here, and then they just kind of respawn infinitely. They train at fixed frame intervals, I should say, not time intervals, because sometimes it runs faster or slower. I want it to be a bit more deterministic. So you see right now they're training. It trains them one at a time, not in parallel or anything, just because that's one of the limitations of using GPU accelerated backend is that none of the structures that allow the GPU to operate or send or sync. So it all has to happen on the main Bevy thread, which is unfortunate because then it has to, kind of pause the simulation while they're training. But it's kind of a side effect of how I'm doing it this way that I've done it. So anyway, enough blah blah blah. Let's get into the code. So I'm actually gonna leave this running while I'm recording the code part, just because I want to see how they've improved by the time I'm done recording this video. Anyway, so it's kind of divided into parts. I kind of excuse me. I kind of have I have the main simulation, which is about 1,000 lines of just Bevy boilerplate. um, it's a lot to go into simulation like this, but and then I have there's actually even more Bevy boilerplate over here with the eGUI user interface, but that's a different story. And then I have the brains. The brains of the agents are kind of what contains the neural networks. And let's see here. Yeah, so brains, yeah, they contain all kinds of stuff about all kinds of like metadata about the actors and the agents. Helper structures like the tensor board writers and stuff. So, and then I have this trait called thinkers, and the thinker trait is what actually does the logic to determine their next action. So that the thinker trait has three associated methods. It has act, learn, and save. And save just saves the state of the neural networks to the disk. Act will pick an action based on observation. I'll get into what that means in a sec. Sorry, I'm a little congested today. And learn will take a buffer of samples of actions, states, rewards, etc., and basically train the neural networks on it. So, as an example, implementation here, I have a random thinker, which just acts completely randomly. It doesn't learn anything. It doesn't save any state. It just picks a random action. So, and as you can see here, I have another thinker in here called PPO. So this is the actual one that you're actually seeing work in this simulation. So what is PPO? Well, PPO stands for Proximal Policy Optimization. I should probably let's see, proximal. I've googled this so many times. I don't know why I didn't just type PPO. But anyway, there's a paper on it. There's a bunch of articles about it. It's a bunch of math. Don't be intimidated, or maybe you should be intimidated because I certainly was at first. But essentially, what PPO does is it takes the observations based on what each agent knows about its environment, and this goes for basically any reinforcement learning algorithm, but I'll get into what makes PPO a special one in a bit. Um, it will take an observation, so things like the agent's position coordinates, the agent's velocity, its rotational angles. Um, it'll take things like how close it is to a wall, things like that, and also information about the other agents around it. Um, and then it will calculate two values. And this is what we call an actor-critic method. And so what the actor does um, is the actor tries, like I said, it takes its input, the observation, and it outputs the parameters to a probability distribution. Basically, it just outputs the actions that the agent should take in that state. That's the essential gist of it, is that without getting into probability distributions and all that, it takes as input the state of the environment from that agent's point of view, and outputs what the agent should do next. Now, the other value that is output by PPO and other actor-critic methods is what we call the critic value, or the value of the observation, value of the state. What that means is that basically, in loose terms, the critic will estimate the possible highest reward that the agent can receive based on the current state. So let's get into that in a bit more detail. Let's see here. So what that means is essentially, how do I explain this? I didn't write a very deep outline before making this video, sorry, so apologies. Yeah, so basically what happens is the actor will predict a action to take in the current state of the observation, current state of the environment. The critic will estimate the amount of reward that the agent can possibly get based on the state, not based on the action, although some algorithms do based on the action as well. And then the actor aims to maximize the reward that is possible from that state, from that state of the environment. So basically, it's a cooperative / adversarial kind of interaction going on with these two neural networks, two completely separate neural networks, mind you, that each are getting the same input but producing different output, but the output of one will kind of influence the output of another. It's hard to explain. It's a complicated algorithm. I'm not going to go into every detail about it right now, but you can read the code on GitHub if you want to see my actual implementation of it. So anyway, let's talk more about what these observations and actions actually look like. So let's go into main.rs, where the environment's defined. So, okay, let's go through these. The observation, this is the actual observation that is input into the neural networks. I mean, it's concatenated into a vector of floats, but either way, it's normalized as well. Either way, what the agent gets as input is its position, its linear velocity, its direction vector, so which way is forward to it, its current health, distance to the walls in the above it, below it, to the left of it, and to the right of it, and then it also gets a list of other states of the other agents. So in the other state, it's just kind of what the agent sees about its opponents. So it sees their relative position. That's their position minus the point of view position. Gets their linear velocity as well. It gets their forward direction, and it gets whether they're currently firing their weapon. So the actions indicate the linear force to be applied to the agent's rigid body. So basically, which direction should it move? Which direction should it turn, its angular force, and whether it should shoot. And that's it. There are 4 variables that the actor can output. As you see, the action length is equal to 4. This metadata is just extra information that's used for training, mostly just what the critic outputs, the value, as well as the log probability of the probability distribution that the actor actually outputs, which I'll get to that in a sec. So yeah, and the rest is just bevy boilerplate. um, Bundles and all that, components, all that good stuff. So let's talk a bit more about the probability distributions. So in reinforcement learning, we have this, and obviously in any kind of learning, even teachers know this and do this. There's this eternal kind of trade-off that you have to find a balance between. And that is the trade-off between exploration and exploitation. So it's, in simplified terms, that just means finding a good balance of doing new things and finding a good balance of doing things that you know are good. So it's like a risk reward factor, Like if you take a risk, you could find something that gives you a bigger reward than what you know about already. You know what I mean? Find a new thing that could give you a nice big reward that you just haven't tried yet. Then again, if you're only doing new things and acting randomly, your chances overall of getting a high reward are relatively slim. So, is that kind of intuitive? Hopefully I explained that right. So, let's go back into PPO to RS. And let's look at these probability distributions. So, because this is a continuous action space environment, meaning that rather than picking a single action to do at any given time step, it chooses the values for multiple actions to take. So, and these actions can be, can be any value in between a certain clamping ratio, right? Clamping, range. So in this case, all the actions are clamped between -1 and +1. So as a result, I use a nice convenient tanh activation for the neural network, at least for the mean mean head, the mu head, which outputs the mean of the probability distribution, and then standard deviation head is activated with soft plus, which will clamp it, keep it from going below 0, because that's just not how statistics works. You can't have a negative chance of something happening, as much as we like to hyperbole about that, you know. So, anywho, so the distribution that I've chosen to parameterize my actions with, and to output the parameters for with my neural network, is a multivariate normal distribution. So, or multivariate Gaussian. If you know what that means, more power to you. Basically, it's just it's a random chance for certain actions to happen. How do I say this? Yeah, let's go back over here. You can see here, it's easier if you can visualize it with this graph that I made. So at any given time step, this shows the current action space output of the actor network for each agent. The height of each bar indicates the mean value, with the average value that will be sampled at that time step. What the range is centered around, basically. And the color indicates the standard deviation of that probability distribution, meaning how random is that action going to be at that particular time step. So green indicates that they're very certain of that action at that point, and that there's a low standard deviation, there's a low variance between what's the maximum action that can be taken and the minimum action that can be taken. And a red bar indicates that the variance is high, that there is a high, that the difference between the maximum action that can be taken and the minimum action that can be taken, again, sampled randomly, anywhere between that range, but that the red bar indicates that that range is very large. And you actually see that numerically here. I know it's very small. Sorry for my mobile users. Um, but if you can see this, you can see that standard deviation ranges between like, 0.2 and probably like like 2 and 0.2 approximately. So that essentially means that when say like the mean is 0.7 and the standard deviation is 0.2, that means that in simplified terms, a random value for that action is chosen in between 0.9 and 0.5. Did I get my math right? Yeah. Sorry. Um, so I'm sorry if that's hard to visualize, but I'm doing my best to explain it. So anyway, yeah. So at every 1,000 time steps, the agents are trained based on a replay buffer, and the replay buffer just records what they're. Here, let's go into that. So that's the thing that I want to cover in this video. The replay buffer will record the observation that was observed at a particular time step, the action that the agent took, the reward that the agent got for that performing that action, and then whether or not the agent died. So, um, and then there's a couple other terms that are calculated on the fly during training, such as advantage, which is generalized advantage estimation. You can look that up if you want to learn more about it. I don't really want to go over right now. And then the actual returns, which is the cumulative reward over time. It's like a cumulative sum. It's a discounted cumulative sum of the rewards that were received over time. That's actually what's used to train the critic network. So the advantage is used to train the actor network. The returns or cumulative returns are used to train the critic network. Anyway, that's enough rambling from me today. I wanted to go over things like log probability and entropy and all that, but maybe that's for another video. My voice is getting a little tired. So thank you all very much for watching. I'll put the code up on GitHub. Actually, it's already up on GitHub. I'll put a link in the description to that. Remember that you can become a member of my channel now that I'm a YouTube partner. Thanks for your outstanding support. So hit the join button if you want to get access to exclusive content, such as little sneak peeks at my projects and little previews of what goes on behind the scenes. If you want to leave a tip, you can hit the super thanks button with a little heart down there. If you have a comment, leave a comment. If you like the video, hit like, do the YouTube thing, and I'll see you all next time. Peace out.